Okay, let's get started. So this is going to be a little different than what we've been doing up to this point. I'm going to talk about a problem called SAT. So, well, it's not the first time we've encountered this, right? But everything today is going to be about Boolean logic. So I think as you all know, we have some basic operations like X and Y, right? True and true is true. True and false is false, right? We have an OR. True or false is true. False or false is false. True or true is true. And we have some negation. True becomes false, false becomes true. Okay. And right, I think I've actually shown this example before, but this would be a Boolean formula that evaluates XOR. So given two inputs, it returns true if you have true false or false true, but not if it's true true or false false. So checking if it's different. Okay, so and I've also shown you this one before. This is the formula for adding two bits together in the sense that it'll return true if and only if x1 plus x2 as two 1-bit numbers is equal to x3, x4 as a 2-bit number. And you can draw this as like a tree, okay, something like this. Okay, so good, right? So this is just breaking it down by parentheses. All right, so you know, although Boolean logic is sort of dry, I want to make the point that is quite expressive. And maybe this is already implicit in the fact that you kind of understand that your computers at the bottommost level is just doing Boolean logic, and at the topmost level, you're finding you can do a lot with it, right? Um, but still, okay. Suppose I wanted to do something first like assignment. So I wanted to write a formula that is true if and only if z is equal to x. So given two variables z and x, let's come up with a Boolean formula. Just and there may be many possibilities. That's true only if yeah. Z bijective x. Oh well, you only have and, ors, and nots. Oh, I got it opposite from you. I did the other way. All right, so I wrote z and x or not z and not x. Yeah, and that one is very easy to read off, right? One of them, they're both true. The other one, they're both false. Okay. All right. How about something like if x, then y, else z? You might need scratch paper or something to do this. Yeah. Sorry, negate this. Uh, or z and z or and. Okay, did I at least write it down correctly? How about another one then? I mean, there's more than one possible right answer. Anyone come up with something different? Yeah. Yeah, so if it is x, let's see. Okay, so this says if it is x and y is true, then it'll return true. If y is false, it'll go to the next one, but then not x will get you to false. So it's okay. So if x is true, it will return y. If x is false, it's going to throw out the first one right away. It's going to go to the second one. And if z is true, it'll return true. If z is false, it'll return false. Okay, so that's probably what I had. Yeah. Okay. All right. But this starts to look like a programming language, right? I can write something for z equals x to effectively assign the value of x to z. I can write things like if x, then y, else z, right? To pick out values and start doing conditionals. Uh, and you can start imagining building up from there, right? Okay, so the only point I want to make is that Boolean algebra is very expressive. Okay, so here then is the problem that we're going to be thinking about. It seems to be like almost a canonical problem for a computer to try to solve. So I'm going to give you some kind of Boolean formula, right? Just x's, ands, ors, and nots. And your goal is to figure out if there's some assignment of variables. You can set x1 to be true, or you can set x1 to be false, x2 to be true, or x2 to be false, such that the formula evaluates to be true. So, for example, here's a simple formula I put at the bottom. Okay, so I give you this formula, and I ask you, is there a satisfying assignment? Okay, I see y. Yeah, okay, so this formula is sort of symmetric. I put in all four combinations of x1 and x2 with knots on them. And, oh wait, yeah. So no matter how you set x1 and x2, one of those pairs is going to have to be false. And since you're doing an and of all these, you'll get false overall. Okay, so there's no way to satisfy this formula. And this is sort of, uh, I cherry picked this because it's also easy to see why the answer is true. In general, it's not necessarily so easy to see why you can't satisfy a formula. On the other hand, if the formula was satisfiable, how could you prove it? Yeah, just any satisfying assignment, say, yes, it is satisfiable. I say, prove it. You give me an assignment and I just double check it, right? So there's already a little asymmetry here. It's actually hard to tell if it's not satisfiable, but you can give, you can convince someone it is satisfiable. So, okay. So, uh, I want to suggest that this is a search problem in a more general sense of the word search, but sort of in the same spirit as the first lecture. Okay, we're looking for something. That seems like searching, but another key feature is that we can recognize it when we find it, right? We're looking for this assignment, x1 to be true or x1 to be false and so forth. But if you do find the right answer, you can double check it pretty easily by just plugging it into the formula, right? If I just define easy as anything that runs in polynomial time, it's not so hard to plug in and evaluate the formula. You should be able to do it, in time linear in the formula. Okay, so you're looking for something, um, right? And so that means that you at the very least have one inefficient algorithm, right? Which is you can always try everything. You can always try everything. It's not an efficient algorithm, but it will be a correct algorithm. You can always try everything and see if something's satisfiable. Okay. But somehow it seems much more complicated uh, than the over-under game, right? So when the over-under game, we're able to, do something simple like guess 50 over-under, guess 25 over-under, and cut the search space in half every time. But it's not so straightforward how to do that for this problem, right? It's hard to identify that structure. Okay, so that's sort of the big question that we're going to be grappling with for the next few weeks. Is there a polynomial time algorithm for this problem? Yeah. What do you guys think? Or any thoughts about this? You can make a what? A tree? Yeah, I mean, you can always take the formula and turn it into a tree. That's not so hard. I give you the tree. But you're still trying to figure out if there's a satisfying assignment for the tree. I note that the tree has some funny features, like we have an example from up above. If you look at the leaves, X1 appears in multiple places, X2 appears in multiple places. So it's not like you can just like separate the tree and say, I'll make the left side happy and then the right side happy, because there's dependencies at the leaves between some of these variables. Any other thoughts? Yeah. Almost, yeah. So would it be too good to be true to get a, what could you do if you could solve this problem? Yeah, almost like any logic, right? If you could just like write down a formula describing a cure for cancer, just give it to the algorithm, and it says, "Oh yeah, yeah, you just plug this in, and there's your cure, cure for cancer," right? So it seems hard to believe that we could solve Boolean formulas because, at least maybe it's more common this day and age to think that many things can be described in Boolean algebra. Yeah. So, right, okay, so I tried to come up with some simple pros and cons. Okay, so maybe why might it be why might we have a good algorithm, or why might one be out there? Well, at least the format is very simple and is seemingly perfect for computers, right? It's just bits, ands, ors. I mean, this is what computers are made of, right? It feels like computers are perfect for this. And what else do I have for pro? It is easy to evaluate the Boolean functions. Okay. And the cons, I think you've already brought up, right? Boolean logic is very expressive. It seems almost like a universal sort of language. So maybe it would be too good to be true. Okay. So let's say it's too good to be true. Okay. I think a natural question from there is to say, okay, is there any special cases we can solve? Maybe we could find some restricted classes of Boolean formulas that we can solve. And okay, you can't write down a description of a cure for cancer or something, but maybe you can do some modest useful things. Okay. All right. So, all right. So now that brings us to a special format of Boolean formulas called conjunctive normal form, which I think is just fancy talk for and of ors. Okay. So these are going to be formulas that's going to be have, a bunch of clauses, and each of those clauses are ors. Pick one of these things, 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 or at least one. And then you're going to do an and uh, across these clauses, right? So each individual clause is very easy to satisfy because it's an or, but you want to satisfy all of them simultaneously. Okay, that's called conjunctive normal form. Okay, so you can think of these as formulas that are like very flat trees. You have sort of one and at the top with many children, and each of these are ors. Okay, so we're throwing out like anything that's very high and right tall. Okay, so okay, so I guess the new question is, given a Boolean formula that's restricted to conjunctive normal form, uh, is it satisfiable? That would be a new problem. We're just restricting the original problem. And what do we have to say about this? And that gives us a more modest question. Is there a polynomial time algorithm for this problem? Okay. Maybe I can take a vote. You guys like votes? I like votes. Votes make the teacher feel like the class is participating even though they're forced to. Okay. So I'm gonna try to figure out um, who thinks there's a polynomial time algorithm and who doesn't for this restricted class of problems. Yeah. You also have the option of not voting. Okay, so who's not voting? All right. Okay. All right. Who thinks that we can get a polynomial time algorithm for this class of problems? 2, 3, 4. There's 4, 5. Okay. And who thinks then we won't be able to get one? 1, 2, 3, 4. 5, 6, 7, 8, 9, 10. Okay, I think I got that right. Is there really 15? 1, 2, 3, 4, 5, 9, 12. Okay, well done. Just twice everyone has voted. This rarely happens. Okay. All right, good. Okay, so if we revise this pro and cons list, I think we're just hoping that maybe this too good to be true um, may not be true, right? It's not clear that they're so broad. Okay, good. Okay, well let's work through. We had these examples before where we took some basic operations and wrote them in Boolean form. Let's turn them into conjunctive normal form. Okay, so let's take this assignment thing, trying to set z to be the value of x. Yeah, so what we wrote is not in conjunctive normal form. Actually, it's called disjunctive normal form, but we want to convert it to conjunctive normal form. Yeah, so who wants to help me do that? Z or not z? Yeah, so a couple of these are, as pointed out, a bit redundant. Yeah, but it's good to show our work. Take it easy. Right, this is like De Morgan's law or whatever, but I'm assuming you've done this kind of thing before. Sure. All right, so that would be a formula for z equal to x. A little harder to read, I think, but relatively compact, is no bigger than before. Okay. How about if x, then y, else z? X or not x, x or z, y or not x, y or z. Yeah, this one is redundant. Ah, okay, something like this. Yeah. Again, a little bit harder to read off. If I directly ask for putting this formula in conjunctive normal form, you tried to do it in one shot. At least I would have struggled with it. But we took a disjunctive normal form, we turned it into conjunctive normal form. Yeah. It got a little bigger, but it's still okay. So here's a slightly better thing. Okay, so at some level, you do at least kind of start replicating Python in conjunctive normal form, right? You do have assignment, you do have if else. You can imagine trying to add some of the other basic operations. Okay, good. Um, okay, so as far as this modest question of is there a polynomial time algorithm for CNF-STAT, even though CNF-STAT is smaller class, we don't know the answer to this question either. Okay, but here's something we can show. There's a polynomial time algorithm for Boolean SAT if and only if there's a polynomial time algorithm for CNF SAT. Okay, so we have these two questions. They're both quite important. We don't know the answer, but we are able to bind them together. Yeah, which is sort of a different way of thinking about things. Okay, we got stuck. We can't solve it, but we can still say something smart about it. Okay, so again, you can get a good algorithm, a polynomial time algorithm for that general problem, if and only if you can get a polynomial time algorithm for the more specific case of CNF SAT. Okay. All right. So yeah, so at some level in the yes or no voting, I guess everybody wins because we don't know the answer, but people interpret this to be a little bit no-ish because they're more pessimistic about Boolean functions. All right, so let's prove this. Okay. One direction is very easy. Which direction is that? Yeah. So if you could do Boolean stat, then you can definitely do CNF stat because CNF stat is just a special case, right? So the interesting direction is the opposite, right? You want to argue that an algorithm for CNF stat will give you an algorithm for Boolean stat. How do you do such an argument? How would you even set one up? Yeah. Okay, so at some level, what we're asking is like, I should draw a black box. If you had a black box uh, that can solve CNF sat, right? And now you have some arbitrary Boolean formula, right? The claim is that somehow you can use this black box. It's going to spit out yes or no for you and tell you the answer, right? But this black box only takes as input things in CNF form, right? So if I can take my Boolean formula and I'll make a new formula, uh, maybe there's different variables and more variables, so I use different notation. Uh, L, right? Which is somehow, I'll put in quotation marks, equivalent to your original formula, right? Like maybe this formula is satisfiable if and only if your original one was. Then I should be able to put that in. I mean, now it's in a proper format for the black box and it could spit out yes or no. Yeah. So if I can convert the Boolean formula into a CNF formula that maintains the decidability or satisfiability, sorry, then you can use your black box. There's one more detail to keep track of though. I can't just turn into any CNF formula. There's one extra, yeah. The conversion needs to be in polynomial time and therefore, and sort of implicitly, yeah. Well, we want the size of the formula to also be polynomial. So as you take your Boolean formula, you're going to make a CNF formula, and you might imagine the size blowing up a bit because you're more restrained in CNF sat, right? So if you're going to have to figure out how to get around some of these constraints, you might have to blow things up. But if you blow things up too much, like you took your formula of size n, you turn it into a formula of size 2 to the n, then a polynomial time algorithm for CNF sat will still give you an exponential time algorithm for the original formula because you gave such a big formula into the box. So we do want to be somewhat economic about how we make this formula. Of course, if you built it in polynomial time, it would almost certainly be a polynomial size because each step you can only add one piece to your formula. So it's sort of implicit in that first answer, but I wanted to draw it out. Okay. All right. So that's our challenge. We want to try to, okay, good. All right. So that's what we're going to do is that we need to come up with a polynomial time algorithm. Right. Well, those are the specifics. It's just what we described. So first, I'm going to first describe the quote unquote size of a Boolean formula. It could basically be how big it is to write it down, right? Just counting up all the symbols, variable or variable parentheses, whatever. And I'm claiming that we should be able to come up with a CNF formula with size roughly m plus n. So it's like number of clauses before plus number of variables or something. Okay. And the total size will be somewhat similar. That maintains satisfiability. So these are pretty tight bounds, to go from m to m plus n and things like this. I wouldn't worry too much about it. That's just sort of what falls out of the construction. If it was like poly m, poly n, I wouldn't really mind. Okay. But that's what we'll show. Okay. So, all right. So what I've done here then is I put up our example of the Boolean formula, and um, how would you convert this into a CNF? Right. This is a little bit bigger than the small things we work through. And the goal is to try to figure out how to do this sort of systematically as well, but maybe just working on an example would be fine. Yeah. If you can come up with CNFs for what are the three, do you mean and or not? Those, well, aren't those already in CNF? Okay. Use De Morgan's. Okay, so can I sort of take the tree, let's say it starts as and at top, and sort of do De Morgan's, De Morgan's, De Morgan's all the way down at some level? Is that the suggestion? Okay. Yeah, yeah. So, or you can do the Morgan's. So I could take the two sub. Let's say that it's a binary formula or something. Maybe try to take the two subtrees. In fact, yeah, let's do that first. As a pre-processing step, just to make our life a little easier, let's assume it's sort of like in binary form. So every time there was more than two children, I kind of broke it up into something. This won't increase the size very much, right? Because if there's n leaves, then there's going to be, n minus one internal nodes if it's a binary tree, but you have a little extra because of the knots, but you don't have two knots in a row, so size will be roughly the same, but it might make the discussion easier. So assume I give you some binary form. Okay, so the suggestion was, can you do something like De Morgan's law? Yeah, is that fair? Okay, so, and then just do it all the way down. So what I'm imagining is something like, let me work in this space. Um, Yeah, you imagine having like an and of two, oh, we're already at the edge, uh, of two things, and then maybe you have an or of more things, and there's an and in here. I'm not sure if these are very helpful pictures, right? But you imagine it's like getting nested down and then just trying to like sort of De Morgan your way out of it, right? You can maybe work from bottom up, okay? Uh, right, so at the bottom, you might have an and of or of two things, or two things, and or you're imagining something like this, right? Alternating back and forth. Okay, now that would indeed flatten it out to a CNF. But did anyone see any potential issues, in particular for a very tall one? Or how big does the formula get? Yeah, it's going to keep doubling. It's going to grow. So this formula can go really big if you're not careful about this stuff, right? Uh, yeah, imagine like an and of two big ors, and then you get all these pairwise things, right? So it's just like starting to square and stuff. Yeah. Okay, so De Morgan's law can actually blow up in size on you. So although you could use that to flatten it out, it will maintain satisfiability. Just using it directly won't preserve the size within a reasonable amount. Okay, so if that's not going to work, then what else could we try to do? Any ideas besides Morgan's law? All right, I have a hint, right? Remember we did this SAP programming language, right? So we have some tricks. Yeah, in particular, we have something like assignment. Okay, that's my hint. So yeah. Okay, so with that hint in hand then, maybe I'll go down here. Any ideas? Or maybe we'll go through it slowly. Okay, suppose I wanted to do something like this, right? I think of this as like, I'm going to evaluate x2 and x3 and assign it to x1. Okay. Yeah, okay, but what is this in CNF form? Or what should I write? We'll work through it. So I guess we're just plugging in this formula, right? And then uh, x2 and x3, uh, oops, or not x1. Yeah. Okay, so I guess this first part is not so bad. Or x3. Did I do it right? No, there's knots here, right? Did I do that okay? For the first one? Okay. And then what would this look like? Uh-huh. Okay. So I think that gets us into conjunctive normal form again. Yeah. Okay. Um, and down here it should be a similar exercise. So the first thing is to just write it out. And x2 or x3 or not x1. Correct me if I do something. I could easily make a mistake. Okay. And okay, so what does this become? This first clause? If you can read my handwriting. X1 or not x2. X1 or not x3. And I guess this one's already a disjunction. And already an or. Okay. So here all we've done is taken our simple assignment and just plugged in the value we want to save. Right? So now you can start doing things like assignment, right? You have this programming language at your disposal. Okay. So that's my hint then. Coming back to here now. Yeah. Right. Okay, perfect. So take this node here. That's a bad color. All right, take this node here, right? And I'm going to call this Z1, right? And I'm just going to write down Z1 is equal to X1 and X2 in whatever conjunctive normal form. We just worked that out, right? And same thing here. I'm going to call this Z2, and I'm going to write Z2 is equal to X3 and not X4 in this example. And then we'll move here, and I'll do Z3, and I'll write Z3 is equal to Z1 and Z2. Yeah. So one by one, we can just replace all the interior nodes of degree 2 in the graph, right? And then we get this formula. This will be like Z whatever. And at the end, you also output Z99 or something, right? So I actually worked through this. I don't even remember how this happened. I think it took a long time. But anyway, okay, so here we've actually introduced all the auxiliary variables and sort of just listed out all the things. There should be an and when it's line wrapping, but you want to satisfy all these disjunctions. And if you can satisfy all these disjunctions, then you can satisfy the original formula, right? Those intermediate values are just, the new variables are just slowing the intermediate computations. Right? It's very much what a computer would do. Okay? Simple enough. Now, how big is this formula we made? How many new variables did we introduce? Yeah, just the number of nodes in a tree, which in particular, relative to number of leaves in the tree, is like the same, right? It's no bigger. So we didn't introduce that many variables. And the formula isn't really that much bigger either, right? Because for every kind of, uh, for every like and or in the middle of the formula, you just introduce a new couple of clauses. Yeah, maybe 3 clauses for each one. Okay. So the size stays the same. Number of variables doesn't grow by too much. And in this way, we're able to come up with relatively small formula in CNF form, right? But there you could also see how useful it is to start having primitives like assignment, right? Once you have assignment and then once you have something that looks like a programming language, even in this itty bitty CNF form, then you could start doing a lot. Yeah? That's how I always remember this trick. Okay, good. So that's the proof then, right? So you take your Boolean formula. To write it out in full, you say, okay, given a Boolean formula, I would construct a CNF formula like this, and I take some time to explain not only how to construct it, but also why the size will look like this. And then I'll take that CNF formula and give it to the black box. And if the black box answers yes for the auxiliary formula we just made, I'll say yes for the Boolean formula in the input. If the black box says no for the CNF formula we just made, I'll answer no for the original formula. Yeah, so just fully explain the whole thing, and then your proof needs to say yes means yes, no means no. That kind of back and forth. Okay. So, but yeah, so you're just showing how to use one problem to solve another. But then that means that this problem in the black box is just as hard to solve in polynomial time as the original problem. Because actually, it's not so hard to convert. Yeah, this is called reductions. You guys have already been warmed up a little bit from the graph problems. Yeah. Good. All right. So if CNF SAT was too general, let's try to make it even more specific. Okay. So here's one called 3SAT. 3SAT is like CNF SAT, but you only have 3 variables, or at most 3 variables per clause. Yeah. And then the question, as usual, is whether the formula is there a polynomial time algorithm for 3SAT? Okay, so even more special case, only 3 variables. All right, who thinks we can get a polynomial time algorithm for this one? Okay, who doesn't think we can get a polynomial time algorithm for this one? Okay, and why? Yeah, so in fact, I think our actual construction only had three variables for each one anyway. Yeah, so you just turn into a binary thing and then you, yeah. Okay. Next time we'll talk about two sat, see how much further we can go. Okay, so three sat also uh, is just as hard as Boolean formula. So not only is it in CNF form, so it's this very flat tree, but you only have three variables in each one, and you're still stuck. Yeah. Yes. So in our case, so the first pre-processing step is to turn into like a binary formula. So everything is like, z is equal to x1 or x2, right? And we just showed in our in our little gadgets here that we only need three variables or less in each clause. Okay. So this will certainly show at most three. Let's say I said exactly three. Okay. Do you think we can get a polynomial time algorithm for exactly three? Okay, say no, but then we have to prove it. So our construction does do at most three, and quite well, right? Now, can we show that exactly three is hard? Hard in the sense that, it would solve Boolean formula. Yeah. Okay, so let's say yeah, just tell me what to do. So let's say I had something with two variables, like A or B. And what would I do? Oh, okay. You can write A or B, but that's boring. Okay. Suppose I told you that you can't, it has to be like three distinct variables. That you can't do. You have to use a variable. You can't add false there. Uh-huh. So what should I write? A or B or C? Uh-huh. You can't just presuppose. That would be setting C to be false. Yeah. Well, that's circular. You might, but I don't know if that'll get us to. I feel like we'll just get back to. Okay, so to clear the problem, we introduce a new variable C, but then they can just set C to be true, right? And then you won't know if they actually satisfied the A or B requirement. Just figure out how to hack the system and get around this. If, yeah, okay, so we'll take each two variable clause and make it two three variable clause with this extra fake variable Z or C, but we'll do C in one and not C in the other, right? So C can only make one of the two happy. The one that's not happy, you'll really find out the truth about A or B. Okay, so this is the kind of the games we play, and then we start understanding connections between these problems. What look like different problems maybe aren't so different. Okay. Well, I guess here they maybe don't look that different, but the the gaps will be more exaggerated in upcoming lectures. Okay, so same ideas. All right, so what about circuits? What is the point I'm trying to make about circuits? Okay, so we also have Boolean circuits, right? We discussed this a little bit earlier as an example of topological sort or an application of topological sort, right? Ands or ors are just arranged as a directed acyclic graph. Okay. All right, so what is the point I'm trying to make? Okay, so in circuit set, I can give you a circuit and ask you if it's satisfiable, right? I can give you a CPU and ask you if there's some way to make the light bulb turn on. Okay, so what is the point I was trying to make? Maybe this is not so surprising, but the claim is that There's a polynomial time algorithm for Boolean SAT if and only if there's a polynomial time algorithm for circuit SAT. Okay. So I guess on one hand, we already knew that a Boolean formula can kind of be drawn as a tree, right? And the only difference between that and a circuit is that x1 can appear in different leaves, right? But I'll just like merge those leaves because now it's a circuit. I'm allowed to do that. So you can go from a Boolean formula to a circuit. That's not very sophisticated. How would you go from a circuit to a Boolean formula? Uh, oh, okay, maybe that's easier. So I'm going to take this x2 and just make two copies like this, gradually convert it to a tree. And you do that all the way through. I'm a little bit worried about things getting big. So this one too has to be duplicated. And that's also duplicating everything underneath. So I'm a little worried that as you do this, you're going to actually, you might get something exponentially big. Uh-huh. No, so I'm worried if we do this thing where every time something has out edges, we start doubling and duplicating for every out edge, right? But then the parents are going to get duplicated. Maybe it's even easier to imagine in a DAG where you've already topologically sorted. And if you have all the edges going forward, right? So the first one gets duplicated like n times, the next one gets duplicated n minus one times, n minus two. I feel like you're going to be in a world of hurt. Okay, so is there another way to try to turn it into a formula? Yeah. Yeah, this we can do. We can do the same trick as before. Z is equal to x1 or x2. And then gradually break this thing apart. All right, so this assignment trick basically solves most of your problems in this space. Okay. Is that true? I don't know. But I think it's good to keep in mind for the homework, which you won't care about until after the midterm, but somewhere in the back of your head. Use the force. Okay. All right. So, oh, we're way ahead of time. That's not good. Um, okay. So, we want, why is that there? But we don't have polynomial time algorithms for any of these problems, right? But they're very natural problems. We wish we could solve them, right? They seem to be very natural. But we actually know that they're equivalent uh, up to polynomial time. Okay, so a polynomial time algorithm for one gives you a polynomial time algorithm for the other. One might be slower. One might be a factor n slower, or a factor 2 slower, or whatever. But a polynomial will stay a polynomial. Okay, so if we define a good algorithm as polynomial, they either have good algorithms or they don't, all simultaneously. Right? Which is sort of an unusual situation to be in. Yeah. No. So to solve these things exactly, there aren't randomized algorithms either. Okay. Well, with any probability, we don't have an algorithm that will solve a SAT formula with probability any better than like, I don't know, 1 over 2 to the n, which is just guessing. Uh, yeah. In fact, okay, here, since you asked, okay, let's look at 3SAT with exactly 3 different variables in every formula. Okay. Suppose we just admit we'll never get an exact algorithm. Well, I don't know if this will make much sense to you guys. I mean, we're jumping ahead to the end of class. Um, Suppose I wanted to get a reasonable approximation. Can you give me an algorithm that guarantees that half the clauses will be satisfied? So you have a bunch of clauses, right? One set of ors, another set of ors, another set of ors, another set of ors. Okay, each one with 3 variables each. Do you have, and so the goal now is not to satisfy all of them because we think that's too hard. The goal is, can you find an assignment that satisfies half of these clauses, each with three variables? Does that make some sense? There's no literature on the whiteboard for this. So you have a three-stat formula. They have clauses. That's the individual parenthesized things with two ors inside of three variables. Okay. And so your goal is think of them as points. You want to get as many points as possible. Yeah. It's not clear that you can get any non-trivial amount, right? Can anyone think of a way to get 1/2 of them, or 1/4 of them, or 9/10 of them? Any number? Huh? I don't know. Well, getting half doesn't mean you can get all of it, right? So at least it doesn't contradict the fact that we don't think you can get an exact algorithm. Yeah. Oh, okay. So here's a silly algorithm. Let me flip coins, okay, for every variable. Now, a particular clause has three chances to get basically a heads, right? Like if it's x1 or x2 or x3, if x1 is heads or x2 is heads or x3 is heads, you're happy. There's only one configuration that's bad. That's 1/8. Okay. So 7/8 at a time, you're going to satisfy any given clause. Okay. And there's something called linear expectation, which will come at the end of class. Okay. But it's going to tell you that on average, you're going to get 7/8 of the clauses in the whole formula. Yeah, you have likely been exposed to this a little bit before. Okay, so you'll get 7/8 just because each clause will be satisfied 7/8 at a time on average. Okay. All right. So here's an unbelievable statement, or here's two exciting statements. One, you can make this deterministic. Okay, we'll do that later. Two, if you can do better than this algorithm, then you can solve Boolean formulas exactly. Okay, so pick any choice. If you could do 7/8 plus 0.0000000001 consistently, okay, then you can solve any Boolean formula exactly. Yeah, so right now the best algorithm, so almost provably, essentially, yeah, provably the best algorithm we have, unless you can solve Boolean formulas altogether, is basically flipping coins. Yeah, in a certain worst case point of view. This is called the PCP theorem. Okay, so this is a very strong theorem. You know, I've never done the whole proof, but we do part of the proof in the randomized class. Yeah, I think we only get to a constant, like, yeah, you know, I think we show in the randomized class if you can do like 0.99999 of the formula, then you can get the whole formula. It takes more effort to get down to 7/8. Um, I will give maybe an analogy uh, as to why you might get something like this, where like a small amount of error can turn into no error. Is something like error correcting codes, right? So when you're sending messages over wires, the wires are faulty, so some bits get flipped, and they want to correct it. So error correcting codes will add redundancy to the code. So if one or two bits are off, it can recover the original message, right? Like it's just like, I don't know, you're talking in the phone and like your grandmother can't hear you, so you just keep repeating the same thing over and over and over again, right? That would be a very primitive error correcting code where you just keep repeating and your grandmother takes like a majority vote of the inputs. What's the most likely thing that I heard, right? But you can do much more subtle redundant things. So you want to minimize the overhead while kind of guaranteeing that you're going to recover the code if at most 5 bits flip, 10 bits flip, things like this, right? And that's the same thing that's kind of going on in SAT. So what you're going to try to do is you're going to take your input formula that you're trying to solve exactly, and you're trying to build some kind of redundant version of the formula so that if you get less than 1/8 error, then you can recover the solution to the original formula because it has some redundancy built in. And there's some technical connections there as well, has to do with expander graphs and whatever. I mean, there's fancy mathematical connections, but it's at least one analogy you can keep in mind. Yeah. Okay, so that's a pretty spectacular uh, thing of a jig. That was in the 90s. they figured this out. So I think in 93, 94-ish is when they figured out there's some constant where you can't approximate SAT better than 0.9999999 or something. Some kind of proof of concept. Any constant is already interesting, right? So there's some limits to approximating algorithms because there was some hope that like, oh, all these problems we can't solve exactly, I can still try to solve approximately, and maybe we can get arbitrarily good approximations, and that's excellent for practice or something. And that was, I think, that made the New York Times. And then I think it was late 90s where they pushed it all the way to 7/8, which we knew was like, oh, that's as dumb as coin flipping. And it's like, oh, there's almost nothing we can do. Okay, but we'll come back to this in proper context. I did any questions though? Yeah. Uh-huh. Oh, okay. Okay, so yeah, when you design hardware, actually, so I think my dad actually works on this. He does SIP verification of some kind. And okay, so then does it become very hard to verify chips? I think it is very hard to verify chips. I think that's why you need a lot of people, is because we don't have an efficient algorithm to do it. And they do lots of different things, including just lots of simulation, randomized testing, and they just try to get it good enough to be stable. Um, yeah, I mean, uh, I don't quite know how they do it. They just poke around. I don't know, see if the light bulbs turn on. Yeah, sure. But parallel won't help you when it comes to, you still have exponential work, right? Because you can always simulate a sequentially any parallel algorithm. So just exponential work is still going to kill you. But I don't think they have super strong guarantees for some of these things that are very hard. But if the chips are very symmetric and relatively simple, this also just says that you can't, only in the fully general case, you can't get perfect guarantee. So what it's really saying is that we don't think you can guarantee a polynomial running time that works for all Boolean formulas. If you're looking at like relatively specific architectures, like a lot of symmetry and like a lot of the same thing repeating or something, a lot of these things can get thrown out the window, right? So we're never really saying anything about specific instances. We're only saying something almost about the nature of maybe the theory of algorithms in general, right? Or it says that we can never quite get, or we don't think you can get a guarantee like we did last week about shortest path or about edit distance or something, which is a very satisfactory, very robust solution. It seems very hard to get something of that form. Yes. Well, why can't we? So people have been trying. Yeah. So if you can show that you really can't do better than exponential time, I think you get $1 million. Yeah. And you'll get at least an A minus in this class. And yeah, so people are very strongly interested. And the only reason I mean, why can't we? I don't know, but like I don't know, people get discouraged after 50 years, right? But people certainly try. And what we're actually going to see more implications of this in the coming classes. This is a big thing. Yeah, right now it feels confined to Boolean formulas, but yeah, I don't want to spoil it, but it's going to expand quite a bit, this world. Yeah. These are great questions. Yeah. Oh, the Morgan's law? Oh, the intermediate levels variables is compact. It keeps things small, right? Um, um, First of all, I'm not sure if I fully appreciate the question. So if you did so is there something wasteful about the Morgan's law? Doing it all the way down? Because we know there's this trick where you insert new variables and you can keep things small. Well, I don't quite know how to answer the question, but I should note that like the Morgan's law, you don't have to introduce new variables. So there's some upside. So there's some trade-off. It's saying that if you insert new variables to capture, yeah, maybe the redundancy, then you can keep things compact. But you have to introduce new variables so you can save, basically save and reuse stuff, right? Yeah. Uh, yeah, what can you do to try to decompose SAT formulas? Yeah, I mean, for some appropriate definition of symmetric. Um, well, I think if you did, you'd have an algorithm, and we don't have an algorithm, so that's one answer to the question. Um, but people do try to. So first of all, actually, people write SAT solvers that seem to work okay in practice. They can't work that well because otherwise you can just tell it to like, generate Bitcoins for you. But like, they seem to work very well for whatever comes up in industrial design or something. Um, uh, and they do a number of heuristics and stuff, and they probably have a big library of kind of pattern matching situations. Um, so they have some strategies that are trying to do some stuff that seem, but I can't fully explain all of them. And I imagine it's a full-time job for a large number of people to kind of just build this growing, expanding heuristic. Yeah. There's also special cases like if the formula is like uh, has certain mathematical properties, and you're guaranteed a solution by something called the Lovász local lemma. That's a famous result. I mean, there's some nice special cases and stuff, but we don't quite have the context for that here. Yeah. Yeah, so the question is, do we have randomized algorithms that uh, get some kind of guarantee to still run polynomial time, things like this? Um, yeah, so the answer is still no. But I should also note that like randomized isn't that magical. For example, we kind of believe that any randomized algorithm should be able to be turned into a deterministic algorithm, even the ones we haven't figured out yet, with comparable properties. Now, there may be some issues like, oh, there's a really slick linear time randomized algorithm, and the best deterministic is still a bit slower, like n squared, but it's still polynomial, and it takes a lot of effort to try to get it down to linear and stuff like this. But that's small beans compared to this kind of question. So randomization is definitely very slick, and it gives you a lot of different perspectives. But it feels like in this setting, it doesn't give you that big of a separation. I think there was a time where we thought, before we understood randomization much better, we're hoping the magic, fairy dust would solve something. But yeah, it feels maybe more magical to you because we haven't had as much practice with it. But other questions? I have some problems queued up to practice, but I'm happy to keep doing this Ask Me Anything thing. Okay. Oh, yeah. Yeah, I mean, you can do 4 sat, you can do 5 sat, you can do 6 sat. The story gets a little tricky with 2 sat, and we'll do that next time. Yeah, in fact, I could take a vote now. So next class, we'll do two problems then. We'll do 2 sat. I'll give you a formula exactly two variables for each clause. Okay. And you have to decide if it's polynomial time or not, or as hard as Boolean formula. And another version of the problem is called max 2sat. So max 2sat, I also give you a formula as two variables per clause, and you want to satisfy as many clauses as possible, not necessarily all. Okay. So you can either say, yeah, maybe we'll just do a vote. Okay. So there's 2sat. This is exact. You're, trying to satisfy all of them. And then there's max 2sat. Okay, so that's two columns. And you have choices. Your choices are polytime or sort of hard as Boolean sat. Some kind of hard, reason to believe it might be tough. Okay, does that, so we're gonna vote on two different things. Okay. But first of all, who's not voting? Okay. Amazing. Good for you. Okay. Does the question make sense? So I'm gonna ask first for exact two sat whether you think we'll get an algorithm or not. And then for max two sat whether you think we'll get an algorithm or not. And then we'll find out next time. What's the truth? Yeah. Okay. All right. So exact two sat. Who thinks we can get an algorithm? One, two, three, four. Are you? Is that one finger vote? Okay. Five or 4.2 or something? Okay. Uh, yeah, I think it's five of you. Okay. So the rest of you think that, okay, so who thinks it's going to be tough? One, two, three, four, five, six, seven, eight, 9, 10, 11. You double voted almost. Okay. Wait, what? 11? No, 10. Okay. All right. Okay. Okay. So more people think it's going to be hard than easy. Okay. All right. Now let's do max two sat. Who thinks we'll get an algorithm? One, two, three, four, five, six, seven, eight, nine, 10. Okay. 10 people thinks we'll get an algorithm, and who thinks we won't? One, two, three, four, five. Five. Okay. So so now for max two sat. So the general feeling is that max two sat might be easier than exact two sat. Okay, well we'll find out next time. Yeah. How does that make sense though? Is it max two sat? Oh, okay. So if you had an algorithm for max two sat, then can you use that to solve exact two sat? Okay, so I have a two sat formula. I want to know if I can satisfy it perfectly, right? If max formula satisfied by max two sat is equal to. Yeah, so I give it to my maximizing black box, and if it says, oh, you can do all of them, then that's my yes. And if it says, oh, the best you can do is all but three of them, then my answer is no. Right? So yeah, you guys got that backwards. Right? uh, so okay. Yeah, good point. Good point. Well, we can end a couple minutes early because I kept you late last time. You're gonna get problems on the homework. You won't care for like 2 weeks. Uh, yeah, you not on the exam. Don't worry about this for the exam. But you're entering an era where you're gonna get problems of the form, either design an algorithm for such and such a problem, or prove that an algorithm would imply an algorithm for something that we think is hard, like Boolean SAT. Yeah, I just refer to as SAT because now we know they're all equivalent, the ones we did today. Okay, but okay, good. And I also note that